next talk will be back to the room, Francesco Segatta. So probably we need to it's better to leave it to professionals.
Yeah, I guess we have to.
So in the meanwhile, good morning to everyone, and it's very good to be here and to be here in presence also, because the last two meetings were online. And okay, I would like to tell you something about what we recently did on the simulation of X-ray spectroscopy with quantum chemistry provided by OpenMolcas. And yes, so I talked about this 2 years ago. Francesco, which will also give a talk today, say something about this last year, and I will talk about some of the latest things that we have done. Okay, so just to give a bit of background for X-ray spectroscopy, why it is very interesting. So first of all, we go with very high energy and interrogate our molecule with very high energy. And so basically we are resonant with the transition of core-electrons. So we deal with core orbitals. And different atoms like carbon, nitrogen, and oxygen have very different binding energies of their core electrons. So we can really spread on a very large window different atoms, and so have an element sensitivity in these techniques. Not only that, but we can also have a site sensitivity. So the same carbon, but in different local environment, can have a shift of 10 eV from this carbon to this carbon. Okay? So we can even distinguish, we have a structural information. And there is also another reason. We are interested in time-resolved techniques. And so here you can have a very, very high temporal resolution, very high, so attosecond timescale, and you can really study, actually they are studying also in experimental facilities, really the electronic dynamics that happens after excitation. And we have, in the last 2-3 years, we have worked a bit on a protocol to compute this, the quantum chemistry of core-excited and core-ionized states. And Francesco told about that last year, but very quickly, basically, is the same protocol that we do for other spectroscopies. We have our molecule, we optimize it, the geometry, we compute the orbitals, we localize the core orbitals, because typically this is a good idea, we can discuss about that. And we then select the active space. And since we are interested in transition that involve core orbitals, we have to include the core orbitals in the active space, of course. And we have to do some tricks to keep this orbital there, because otherwise it's not there outside. And typically in RASS2, so we use the RASS let's say, and in RASS1 we put the core orbital of interest. In RASS2 we put some valence occupied orbitals, and in RASS3 we put empty molecular orbitals that can be the arrival orbitals of our excitation. So then in the core valence separation approximation, we have two sets of computation that we have to do. On the one side, we have to do the valence computation for example, the ground state that we want, that is our starting state. And then we have to compute the core-excited or core-ionized states. And to do that, we cannot have a state average with, let's say, 1 billion states, and the 1 billionth is our core-excited state. We have this implemented, not we, but it is implemented in OpenMolcas, this hex keyword, which is highly excited state keyword. And basically, it's a strategy to project out from the wave function, so to set to 0 all the CI coefficients that have a double occupation in our RASS1 space. So it means that the first relevant configuration has a hole in the RASS1, so in our core orbital. And with that, we can specifically target core transitions. Then with RASSCF, we can we can compute transition probabilities between our ground state and our core-excited states. And we can also, if we want, and I will talk a bit about it, compute the vibronic coupling between the transition and the intramolecular vibrations. This might be important for a quantitative description of our line shapes. We send all of this information through an interface that we developed, and at the end we compute the spectra. And this is, for example, for XANES, which is linear absorption in the X-ray window, in which we have bound states. And similarly for XPS, in which we really eject the electron out, we ionize the core orbital. We just have, instead of transition dipole moment, we have Dyson intensities, and instead of the core excited states, we have core ionized states. But it works pretty much the same for XANES, so linear absorption, and XPS, which is photoelectron spectroscopy. So just to give a few examples then of the application of this method, we first studied this molecule, which is the ESCA molecule, which was actually specifically designed and built to show the capabilities of X-ray spectroscopy. It is called electron spectroscopy for chemical analysis. So it was really invented for that. And you can see that the four carbon atoms have different chemical environments. And indeed, by doing the XPS spectroscopy, so photoionization in the X-rays, one realizes that the spectrum is described by these four bands, well separated, 2, 3 eV from each other. And yes, the four bands, basically each band pertains to a different carbon atom. And theoretical calculation, which are the arrows in the plot, basically reproduce the results that we have in the experiment. And if we go to linear absorption, instead of XANES, it is interesting because the spectrum becomes much more complex. And we have also, so it's much more complex, and it extends. Is there a laser pointer? You can use this. Ah, okay. No, it's okay. So you see that. Oh, you can see that it extends more in the red, and this region in the red is called pre-edge region before the first ionization. And the XANES bands overlap, and also our theoretical calculation that we have the spectra that I show that now the different carbons contribute in very different regions of the spectrum. So we have not the clear separation that we had before with XPS. So we want to have some chemical insight. It's pretty simple once one think about it. And why are there multiple bands? Why the XANES spectrum is more complex? And the idea is simple again. So for XPS, so ionization, basically the only thing that matters is the energy of the 1s orbital from which you are extracting the electrons. And since the different groups push or pull electron density from the carbon of interest, this reduces the shielding, for example, of the nuclear charge. And so extracting a core electron from the carbon with the 3 for an atom outside that pull a lot of charges costs more energies with respect to extract the 1s electron from the other carbon. And instead, when we go to XANES, we have not only to care about the initial, let's say, the starting orbital, let's say, but also we have a lot of possible final orbitals in which we promote the electron. And so we have to consider both things, and both contributes. And since you have now the energy of the starting orbital and the energy of the final orbitals, and not all the transitions are bright in the same way, you have this basically scramble of the transition that occupy all the spectrum. So XANES is richer in information, but is also more complex, let's say. Then we wanted, this was done basically just without any coupling to vibrations, but we want to understand a bit the coupling to intramolecular vibration of these transitions. And here you can see we studied a series of fluorinated ethylene molecules. And here you can see on the left, we didn't include the vibrational coupling, and we just address basically our sticks with the lifetime governing. I have to say the lifetime of these states is pretty short because you have injected a lot of energy in the system, which very quickly breaks apart, for example. And you can see that including the vibronic couplings greatly improves the line shape of the spectra. And we use a simple model for including the coupling to vibration, which is the displaced harmonic oscillator, or the vertical gradient approach. Substantially, we only compute the normal modes for the ground state. We compute the excited state gradient for all the states of interest. And the excited state gradients tell us how much displaced is the excited state well with respect to the ground state well. This within certain approximation. We are assuming harmonic wells. We are assuming that the same set of frequencies that we computed for the ground state is okay, and normal mode is okay for all the states, is the same for all the states. And we are also assuming in our calculations that the transition dipole moments do not depend on the coordinates. It is interesting that in core transitions, these approximations are particularly wrong, in the sense that we have to ask ourselves, what happens when we extract one electron from the core orbital? What happens, let's say, on the electronic structure level? How does it influence the bond into the neighbor atoms? And how does this eventually impact the line shape? How many minutes do we have? 7, 5. Okay, we'll go a bit fast here. So basically the idea, if we think what happens when we extract one electron from this 1s orbital, now there is, instead of V, the nuclear charge, which was shielded, let's say, by all the electrons, and especially the core electrons, we basically remove one electron from the 1s. Now the electrons above feel a much stronger attraction. Okay, so we have a kind of reorganization of the electronic density towards the nucleus. And this we can think that this basically changes the way the atom bonds to its neighbors, because of this relaxation towards the nucleus. For example, if we have in the non-nuclear case 2 carbon atoms, and we excite one of the two, all the orbitals will lower, let's say, in energy, and we will weaken the bond with the nearby carbon. But if we have, let's say, an heteronuclear case, it really depends if we excite the carbon of the fluorine, because if the molecular orbital diagram we start with is this one, and if we excite, let's say, the carbon, we lower the energies of the orbitals that makes the bond, and so the bonds may strengthen. But if we excite the fluorine, we, let's say, weaken the bond even more. And so ground state and core ionized state frequencies are different. So the displaced harmonic oscillator is particularly wrong. And we have a strengthening or weakening of the bond that depends on which atom we are ionizing and which atoms are around it. And this is a fact when we just extract the electron, so ionization. If you consider, let me skip this part. I cannot skip it. Okay. Now, it was just basically, we realized that because we had systematic errors in our theoretical estimation with respect to experiments. And since we trust a lot the quantum chemistry we were producing, all the people typically do shifts. We didn't do shift, and so we have a shift. Why do we have it? And we realized that this was related to this thing that I just said. So the fact that excited state frequencies are different with respect to ground state frequencies. And we can explain the trends of carbon being redshifted with respect to experiment and fluorine being blue shifted because of this frequency shift. But if we go to excitation, so not really just ionization, but excitation, we have the thing that I've just described for ionization, but we have also the fact that we relocate the electron in an anti-bonding orbital. So we can, if we put it in a Rydberg orbital, nothing really happens, but if we put in a pi star or in a sigma star, we have a further weakening of the bond. And we observe that in XANES spectra. For carbon, it is interesting because we have said that removing a core electron, for example, here in ethylene, would strengthen the bond between the two carbons. But then relocating it in a pi star or in a sigma star will weaken the bond. So at the end, the two effects contrast each other, and the displaced harmonic oscillator allows you to describe basically the line shape quantitatively. Instead, in fluorine, removing in this system, for example, removing one electron from the core of the fluorine weakens the bond, and relocating it in a sigma star orbital even more weakens the bond, and so you have dissociation. And the fact that this experiment is not reproduced very well by our simulations. The line shape is completely different because of that. Then, and this is the most recent stuff, we want to move towards larger systems. And so we want to really, because these were very small systems in which we can do whatever we want. And so we tested a few strategies. In particular, many people say, okay, you can use RASSCF or SPT2, but typically for realistic system, you cannot do that because it's too costly. But what we tried is, okay, let's see if it is true. And we try to basically reduce the active space to very small active space that only includes a very small number of orbitals and see how this affects the line shape. Here I'm reducing, if you see the number of virtual orbitals, so from 10 orbitals that are in the first step, in the second step there are 6 orbitals, in the third step there are 4 orbitals, and in the last step there is just the pi star orbital of this 1, 1, 4. You see that, very interestingly, the most relevant pre-edge transitions are well reproduced just with a very minimal active space. And this is related to the nature of the transition that we consider that are mostly single configurational in nature. So really, typically having the single configuration with the core orbital and the arrival orbital is enough to describe them very well. And if we add the vibronic coupling, you see also the intensities that were not that good improved. But the other thing that we did was to move in the other direction. Let's say we start from a minimalistic active space and we want to have spectral completeness in a certain window that we are interested in. And how do we do that without considering an extremely big active space? We thought, because leveraging of this, the fact that the core of this transition is described by single determinants, let's say, we don't have to include necessarily too many, I mean, the wave function is not too much multi-configurational. What we did was, okay, let's consider a minimalistic active space. Let's add to the active space a small number of virtual orbitals, let's say 2, a chunk of virtual orbitals, let's say 2. And let's do the computation with these. And then what we do is we push these orbitals that we used outside of the active space. We put new orbital inside. We lock the one that we already used, and we repeat this computation serially until convergence, spectral convergence, let's say, of our simulation. And what we tested it again for a very small molecule. And you see, if we consider the very small active space, the line shape is not very well reproduced because we are not including enough, let's say, transitions to describe the spectral window. But then let's say we apply our protocol and we do more computation, and at the end, especially if we include the vibronic coupling, you see that at the end, with the sequence of serial computation, we reach again a very good description of the line shape. So, of course, there are approximations. If you want, we can talk about this. With that, I just wanted to show a bit this effective quantum chemical computational protocol to simulate a variety of X-ray techniques, single spectroscopy techniques. In particular, we have recently published this JCTC paper that summarizes what I've shown you today. And the quality of the quantum chemical data is extremely high, so we can look at deviations and say why there is a deviation, not just shift to, again, go on the top of the experimental spectra. And we have shown this divide and conquer approach to reach spectral completeness. And in the afternoon, Francesco will show you an application to a larger system, this nicotinamide adenine dimer, and to time-resolved X-ray spectroscopy. And with that, I thank you for your attention, and if there is any question. Yeah.
We have time for, well, okay, we have time for 2 short questions. Miguel first.
So as you described, you're finding very similar reference with each mutations. So actually, what is the motivation for using RASSCF in the first place?
Yeah, so I've said that, let's say, the gross part of the wave function is described by this single. But then there are a few things. So first, there are so-called shake-up features which are states in which not only you have this, you have really, they are dominated by, for example, a double excitation character and a small single excitation that gives you a bit of intensity. This is important to describe, and we want to describe first. Second, I said that it is the gross part is described by that, but actually it might be important also that for the intensities especially to have the let's say the double, the triple, and the quadruple. Even the quadruple might be important, especially because maybe instead of having 90%, we have a test on glycine molecule. We have a transition that was there with single reference method that we didn't see, and we went there and we analyzed where the quadruples that were basically lowering the percentage of the single electron transit, and so basically in the intensity of the band distribution. But in general, the gross features are described by single excitation. There are cases in which it is important in multi-configuration.
Yeah, so I don't know whether it's a question or a comment. So you have said that the shifts in the spectra, they are unique to the effect.
Yeah.
There is a community where we struggle to reduce the shifts to purely electronic methods. So my question is actually if one uses a method which doesn't have shift into the electronic method shift, and then one goes to the spectrum shift.
So actually the shift that they have are of few EV. Still of few EV. The shift that I have are sub EV. So this is the first thing. The first thing that we realized was that just doing the stick spectra, we were basically online with the experiments. Instead, they have to do sometimes red shift, sometimes blue shift. It's not even the same for all the atoms, but this is okay. And I mean, you change the level of theory, you change the level of the shift of theory. Instead, what we realized was, okay, we are very, very close to what is already there in the experiment, but we have small deviation. And we realized that they were systematic according to the atoms and the bonding network. That's why we point towards, okay, maybe it's a bond and happening to the nuclear effect. And we went there and we realized that accounting for that was explaining the small shifts that we were obtaining. This is the key of having a method that already basically is so precise that what is the deviation, you can try to understand what it is instead of just shifting. This is,
in other words, like your already is that why the sequence which you described or the particular lack of covalence
which are approximation that everyone do. So at the net of the same approximations, I see that this level of theory brings you so close to the actual result that what is not and is systematic, you can try to understand what it is. Which was, I mean, in the, but it really looked like that, and but in the publication you will find more information and also comparison with other methods.
Okay, so let's thanks.
Thanks.